Welcome to this class on bearing capacity of shallow foundations for Geotechnical Engineering 2. I hope all of you are keeping well during this lockdown time. Stay safe, stay home and continue your studies. So first of all, let us introduce what is bearing capacity. Now when we design a foundation for carrying some loads from the superstructure to the soil, as an engineer we need to ensure that the foundation can transmit the load safely, and the safety means in the context of geotechnical engineering that the soil beneath the foundation should not fail due to shear failure of the soil, and also the superstructure or the substructure or the foundation, substructure and foundation are same thing, meaning the structural footing, and we need to ensure that the soil does not fail below the foundation, and the structure as well as the substructure does not suffer excessive settlement. And therefore when we talk of the bearing capacity, that means the capacity of the soil to bear certain load from the superstructure, ensuring that there is no shear failure of the foundation soil, that means the soil nearby the substructure or the footing, and also the structure does not suffer any excessive settlement. So that capacity we need to calculate depending on the soil type and foundation type. So it is the pressure or the stresses that can be safely applied at the soil foundation interface so that there is no shear failure of the soil and there is no excessive settlement of the structure. That is what is called bearing capacity. Okay. Now when we talk of bearing capacity, calculation of bearing capacity, usually we refer to the shear failure criterion just now we have discussed. And the pressure which is obtained on the basis of the allowable amount of settlement, that is called the allowable bearing pressure, the bearing pressure. Okay, so both are different, and as an engineer we need to ensure that both these two criteria of failure can be fulfilled. That means our foundation neither fails due to shear failure of the soil nor it undergoes any excessive settlement. Now there are some usually applied terminology. Suppose I have a footing here and we call it a shallow foundation. Now a shallow foundation is defined as the one whose depth of foundation, shown here as df, is less than or at the most equal to the width of the foundation, which is denoted by b here. Okay, this was the definition given by Terzaghi and has been universally accepted. So in shallow foundation we basically don't rely upon the side soil resistance to resist the load. primarily we resist the load through the resistance of soil below the foundation. Now, related to this, there are few basic terms which we must understand before we go into details of bearing capacity calculation. The first one is called gross bearing pressure or the gross load intensity. It is denoted usually by Q, and it is the total load intensity, that means the total stress that is acting at the soil foundation interface, that means the base of the foundation. And this level is also called foundation level. This is my ground level here, and this is my foundation level here. Okay. So this gross pressure includes the load coming from the superstructure, which is shown here, and also the load due to this overburden pressure at the foundation level. So the gross pressure is sum of this pressure due to the superstructure load from the superstructure and substructure, and the surcharge or the overburden at the foundation level. Then we have the term called net bearing pressure. So this net bearing pressure is the pressure that is coming only due to the structural load at the foundation level. So it excludes the effective overburden pressure or the surcharge from the gross pressure, and that is called net pressure. So net pressure is given by the gross pressure minus the surcharge, which is denoted by Q naught here. Okay. Now at the verge of failure, whatever gross pressure the soil can take will be called as gross ultimate bearing capacity. It is denoted by QU. U stands for ultimate. So it is the gross load intensity at the foundation level which causes the shear failure of the foundation soil. That means soil will be at the verge of shear failure. Okay. Then similarly, if I take the net pressure at that condition, that will be called net ultimate bearing capacity. So net ultimate bearing capacity is the net load intensity at the foundation level which will be sufficient to cause or initiate shear failure of the foundation soil. So it is, again, we can write it as the difference of gross ultimate bearing capacity and the effective surcharge. Okay. So for example, we can write that, say, Q net ultimate will be equal to Q ultimate minus the surcharge. Okay. So this is how we can express net ultimate bearing capacity. Fine. So next, we need to design our foundation so that we are safe against shear failure and also we are safe against excessive settlement. Now, accordingly, we define net safe bearing capacity, which is the net ultimate bearing capacity divided by a suitable factor of safety. Okay, that is called net safe bearing capacity, and it is denoted by QNS. That means Q net safe. and the safe bearing capacity is the gross safe load that can be placed without causing any shear failure, without the risk of shear failure, and therefore Qs will be the sum of Qns plus the surcharge, which is Q naught, which is given by the density times the depth of foundation. Okay, so these are some of the important terminologies which will be frequently used when we talk of bearing capacity, and we must understand these definitions very clearly. Now, since I need to design my foundation to be also safe for settlement criterion, therefore we also define another term called bearing pressure for allowable settlement. So it is the net pressure that causes the foundation to settle by the allowable value of the settlement. Usually the allowable settlement for building foundations are taken as 25 mm, approximately 1 inch, or in some cases up to 40 mm are also possible. So whatever pressure that can be safely put on the structure so that the allowable settlement is not exceeded, that is called bearing pressure for allowable settlement. And ultimately we need to find out the net allowable bearing pressure, which is the lesser of these two, the net safe bearing capacity or the bearing pressure for allowable settlement. Whichever is lower, we must limit our load intensity to that amount so that we are safe both from shear failure criterion and from the settlement criterion. And that's why the allowable bearing pressure, net pressure, will be equal to Qns if Qns is less than the bearing pressure for allowable settlement, and it will be equal to bearing pressure for allowable settlement if this is smaller than the net safe bearing pressure. So this is obvious. So lower of these two values we recommend as the net allowable bearing pressure. I am sorry. Now this bearing capacity of a foundation, shallow foundation, usually when we talk of bearing capacity, I told you already that we refer to the shear failure criterion. So it depends on how the shear failure takes place below the footing, how the soil fails in shear. Now from experimental studies, it has been found that a shallow foundation usually fail by one of these three modes of failure. The first mode is called general shear failure. The second mode is called the local shear failure, and the third mode is called the punching shear failure. Now let us discuss each one of them to some extent. Now in general shear failure, what happens is it occurs in dense sands or stiff clays, and we have some well-defined failure surfaces that extend up to the ground level. So when we push the foundation, there is some portion of the soil, a wedge of the soil, that behaves as a part of the foundation itself, that is called elastic zone. The soil remains within elastic state in that zone. Then my shear failure surfaces develop in this manner, and these shear failure surfaces extend up to the ground level in case of general shear failure, which occurs in dense soils, namely dense sands and stiff clays. Okay, and we can find, if we draw the load settlement curve of the foundation, we can get a clearly defined peak load, okay, before failure. And after this load is passed, then settlement increases indefinitely. And therefore the failure is sudden and catastrophic. We have a distinct failure load in this mode of failure, and there will be usually considerable tilting of the foundation, and also there will be bulging or heaving of the soil near the foundation at the ground surface, and this heaving is quite prominent in case of general shear failure. And there will be excessive settlement that will go on after the failure has occurred. You remember the stress strain curve of dense soil, dense sand interaxial test. So the load settlement curve looks similar to the stress strain curve of dense sands in this case. The other mode of failure is called local shear failure, which occurs in soils of medium to loose sands whose relative density is in between 70% and 35%. I forgot to tell you that general shear failure usually occurs when the relative density is above 70% in case of sands. Now coming to local shear failure, it occurs in medium to loose sands whose relative density lies between 70 and 35%, and also it occurs in moderately stiff clays. And we have, like general shear failure, we have well-defined failure surfaces below the foundation, and it extends up to the ground level, but the lateral extent, the distance, lateral distance up to which the failure plane goes, that is less in this case than the general shear failure case. You can see it here, this width is more than in this case. Soil more close to the foundation is only affected by bulging, and the amount of bulging is less in case of local shear failure than in case of general shear failure. And mainly the settlement will take place beneath the foundation, and there will be less amount of bulging, as I have already told. And we do not see a very well defined peak failure load like that was seen in general shear failure case. So that is what is called local shear failure. And the third type of failure is punching shear failure, where actually the foundation punches the soil. It doesn't affect the side soil, so resistance of the side soil is not taking place in resisting the load, and the soil only directly beneath the foundation is only taking part in providing resistance to failure. And that is what is called punching shear failure, and it occurs in very loose sands where relative density is less than 35%, and it also occurs in soft clays, and the settlement is, the soil that is affected by settlement or straining is only directly beneath the foundation. Side soil is not at all affected, and there is no bulging or heaving at the ground surface, and the failure surface in fact does not goes up to the foundation level. That's why we're saying that the soil below the foundation does not actually takes part in resisting the load in this case, and accordingly we don't have any clear load at which the foundation fails. We have to decide based on the amount of settlement. So this is what is called punching shear failure. So these are the shear failure modes, namely general shear failure, local shear failure, and punching shear failure. Now of course these modes of bearing capacity failure, whether a foundation will fail in general or local or punching shear, that not only depends on the density of the soil, it also depends on the relative depth of foundation, which is the ratio of depth to the width of the foundation, and it also depends on the relative width in case of, say, rectangular foundation. This figure was given by Vesic in 1973, who studied a number of foundation failure cases, and he found that these are the zones in this graph where relative density is plotted from 0 to 1 in this direction, and relative width is plotted, and in this direction relative depth of the foundation is plotted. And we can see that if the soil is loose and the depth is higher, then even say for this case, if the depth is more, then there will be punching shear failure, but for the same relative density, if depth is less, then there may be local shear failure. Similarly, for the same relative density, I may have, depending on the depth and width, I may have either general shear failure or local shear failure or punching shear failure. So it depends on number of factors, the mode of failure. Okay. Now there are different bearing capacity theories to calculate the bearing capacity of foundation based on limit analysis, and most prominent of them is obviously the Terzaghi's bearing capacity theory, and there are some other theories given by other researchers like Meyerhoff, Brinch-Hansen, Vesic, etc. So we will see briefly what are the characteristics of these theories, bearing capacity theories. Now, when a foundation fails, a real foundation fails under the action of an increasing load, the actual failure surface cannot be exactly predicted. Therefore, different researchers have assumed different possible kind of failure surfaces which may develop below the footing during the general shear failure case. All right, and of course these assumption of these shapes have been inspired by experimental tests on actually failing foundations, model foundations, and the difference between different failure theories, different bearing capacity analysis, mainly differ on the basis of the assumed shape of the failure zone. Now, what Terzaghi and all other researchers have told is that this triangular shaped wedge directly below the footing remains, the soil within that portion remains in elastic condition. That's why it is called elastic wedge, and the soil outside the elastic wedge at the verge of shear failure undergoes plastic equilibrium. That means the soil is at the stage of plastic failure, and this zone, which is denoted by zone 2, this is characterized by some spiral kind of failure surface. Usually they are assumed to be logarithmic spirals, and the zone 3 here, this portion is called Rankine passive zone. You have not studied earth pressure coefficients yet. When we will study earth pressure coefficients, we will come to know that there is something called passive earth pressure. When something pushes the soil against its original location, then the passive pressure occurs, Here what is happening, the footing is pushing, footing is moving down, this elastic wedge is pushing here, this is also passive, this is also passive, so this soil is being pushed by this elastic wedge, and therefore this everything is in the passive pressure, but this zone is, it is called zone of radial shear because the shear failure surfaces radiates from the edge of the footing, and here the shear failure surfaces are parallel, and this angle is, as per the Rankine's passive earth pressure theory, it should be 45 minus 5 by 2, and that is what is assumed by Terzaghi and Hansen. And in the bearing capacity theory given by the Terzaghi, the soil resistance above the foundation level is neglected. On the other hand, in Meyerhoff's theory, he assumes that this whole portion is, this whole failure surface is made up of logarithmic spiral curve, and he also includes the resistance above the foundation level up to the ground level. He also includes in his calculation the shear resistance along this portion of the soil, which is not done by by Terzaghi and Hansen. And there are some differences in the details of this geometry. These are written in this figure. This is taken from Bowles' book. And so here also it is shown that Terzaghi and Hansen has neglected shear along this portion. And that is how these various bearing capacity theories differ. Okay? These are as far as the calculation of bearing capacity from the very preliminary analysis, but as an engineer we never do this kind of analysis. We use whatever are the solution given by these researchers, Terzaghi, Meyerhoff, Hansen, Vesic, etc., while calculating the ultimate or net ultimate bearing capacity. And in a moment from now we will see how to do that. Now these are the things, it is written in this slide which we have already discussed. As we gradually increase the footing load, initially the soil reaches the elastic limit, and then shear stresses reach the plastic shear strength as per the Moore-Coulomb failure theory or other plastic theories, and at the ultimate load the plastic failure occurs in the soil. That we have already discussed, that these portions are under the state of plastic equilibrium, right? And we have already discussed what are the primary differences among these various researchers doing the bearing capacity analysis. Okay, and all of them have expressed the ultimate bearing capacity, that means gross ultimate bearing capacity, as sum of three parts, and this sum of three parts are due to the soil resistance of an idealized weightless soil contributed by the cohesion present in the soil, if the soil is a C5 soil or cohesive soil. Then the other part is coming due to the surcharge of that weightless material, and the remaining part is coming due to the frictional resistance of the soil having weight. All right, so the ultimate bearing capacity has three components. One is due to the cohesion part of an ideal weightless soil where the effect of weight is neglected, that means. Then the frictional resistance of a weightless soil only due to the surcharge, and the frictional resistance of a soil which has the weight. And in this manner, when they express the ultimate bearing capacity, they express them in terms of some dimensionless numbers. These are called bearing capacity factors. This NC is the bearing capacity factor related to the cohesion component of the resistance. This NQ is the bearing capacity factor related to the surcharge component of the resistance. And N gamma is the bearing capacity factor related to the resistance, frictional resistance coming due to weight of the soil. And they are PO numbers. They are dimensionless numbers which depend on namely the shear strength parameters of the soil, namely the phi. So for us average engineers or the practitioners, the life is much simple now. If I know the phi value of the soil, I can find out these PO numbers, bearing capacity factors, and I can put them in this simple looking equation, and thereby I can get the ultimate bearing capacity, or rather we prefer to find out the net ultimate bearing capacity. So in the net ultimate bearing capacity, there will be a negative Q naught term here, all right, because net is defined as gross ultimate minus the surcharge. So that is taken common here, so it can be expressed as C and C into Q naught into NQ minus 1 plus half gamma B N gamma. Okay, so this is the form of bearing capacity equation given by Terzaghi and also given by other researchers. The only difference is that the values of these bearing capacity factors differ from researcher to researcher, authors to authors. Okay, that is the only difference. Okay, now these are the values of bearing capacity factors given by Terzaghi for general shear failure condition. So here we have angle of shearing resistance phi in degrees, and this curve is giving me the value of NC here. We can read the value of NC if I know the phi value, and I can put in that equation. Similarly, I can use these curves for N gamma and NQ. By knowing the value of phi, I can find out the values of NC, NQ and N gamma, and then we can use them in this equation to get the net ultimate bearing capacity. All right. Similarly, these are bearing capacity factors given by Peck, Hanson and Thornburn in 1980s, which also includes the SPT values of the soil. So based on the SPT results, we can directly find out the bearing capacity factors and also the phi value of the soil from the SPT, and thereby I can calculate the ultimate or net ultimate bearing capacity. Okay. One more thing I think I forgot to highlight, and that is this net safe bearing capacity is given by net ultimate bearing capacity divided by the factor of safety, and then the gross safe bearing capacity is just the sum of net safe bearing capacity and the overburden pressure or the surcharge. Note that we do not divide the surcharge by the factor of safety to find out the gross safe bearing capacity. So that is important to note. Okay. Now coming back to what we had been discussing, the bearing capacity factors. So these are the bearing capacity factors which can be read directly from the corrected N value of the soil. Then let us see what are the various factors that affect bearing capacity of a foundation. Now these bearing capacity factors, as I have told you, are based on the assumed failure surfaces below the strip footing. Usually they have assumed a strip footing so that plane strain condition can be assumed, and the analysis has been done. And this analysis is done for the failure surface that takes place in a general shear failure condition, and with the assumption that the groundwater table is not affecting the calculation because the groundwater table is at a large depth. Therefore, whenever these factors are different in a real foundation, then that is obviously going to affect our bearing capacity of the actual foundation. Therefore, the factors affecting bearing capacity can be listed as these. Number one, the shape of foundation. If the shape of foundation is not of strip footing, then the bearing capacity factors are to be corrected. Similarly, these bearing capacity factors were obtained for vertical load. If in the foundation I have some inclined load, how can inclined load come? Actual load on the foundation can be inclined if there is a horizontal component of the load, like that for earthquake load or wind load. When they are combined with the usual vertical dead load or live load, the resultant will be inclined. And due to this inclination, I have to correct my bearing capacity calculation, and therefore the inclination of the load will also affect the bearing capacity calculation. All right. Then depth of footing, of course. Then the location of groundwater table, as I have already told you, and also the type of shear failure, whether it is general shear failure or local shear failure, that will also affect the actual bearing capacity. Now let us come to a bearing capacity equation that takes into account all these factors that we have just now mentioned. Now our IS code, IS 6403 1981, it was reaffirmed in 1997. This code recommends a general bearing capacity equation which is based on Meyerhoff's results in 1965. So it takes into account these factors: shape of the foundation, inclination of the load, depth of the footing, location of the groundwater table, and also type of shear failure. And this equation is given as this: the net ultimate bearing capacity is the same as the general earlier shown bearing capacity equation, but they are multiplied by some correction factors due to the shape of the footing, depth of the footing, and inclination of the load. And these factors are again divided into those various components that we have already discussed resisting the load by the soil: the cohesion component, the surcharge component, and the weight component, frictional resistance due to the weight. So we have SC, which is the shape factor taking into account the cohesion component, depth factor DC, and IC, which is the inclination factor considering the cohesion component. Similarly, I have SQ, DQ, IQ, and S gamma, D gamma, I gamma. These three sets of factors are taking into account the shape, depth, and inclination factors of the footing. Okay, and this RW, Q, and RW gamma are the correction factors for location of water table. They are also divided into two components. One is the component affecting the surcharge, and one is the factor affecting the frictional resistance due to weight part of the total resistance. So general equation for net ultimate bearing capacity looks like this: C and C, SC DC IC, then Q naught into NQ minus 1 into SQ DQ IQ into RWQ, and half gamma B N gamma S gamma D gamma I gamma into RW gamma. And these values are specified by our code. Now let us see what are the values. First, the bearing capacity factors that are given by IS 6403. We need not refer back to those charts if we follow this bearing capacity equation, because they are expressed in terms of some analytical formulae. NQ is given by e to the power pi tan phi into n phi, where n phi is this value, tan square 45 degree plus phi by 2. Then NC is 5.14 when phi is 0, otherwise NQ minus 1 cot phi for phi greater than 0. And N gamma is given by 2 times NQ plus 1 into tan phi. So these are the formulae given for bearing capacity factors by IS 6403. They are easy to remember, so we don't need to look or depend on those graphical charts. Okay. Sorry. Then the values of shape factors are given by IS like this. SC is 1 plus 0.2 B by L, where B is the width of a rectangular footing and L is the length of a rectangular footing. And when it is the footing is circle or square shape, then B and L are equal. B is the diameter of footing for a circular footing, but the value is not 1.2 but 1.3 for circle and square. These are based on Meyerhof study actually. Then similarly SQ is also same, but it is equal to 1.2 for circle or square. For rectangular footing it is 1.2 B by L. And S gamma is 1 minus 0.4 B by L, and that is equal to 0.6 for circle but 0.8 for square. So these values we need to remember because they don't follow exactly these formulae. So these are my shape functions given by the IS code. And let us note that in the bearing capacity equation, general bearing capacity equation, if all these values are 1, then we get back the equation given by Terzaghi or Meyerhof or Vesic, etc. The original equations. So that means all these factors assume a value of 1 or unity for strip footing. Okay. So that's how we can look at it. So for a strip footing, all these factors SQ, DQ and IQ have a value of unity. Next, let us go to the depth factors. Depth factors are defined by these equations. Then we have inclination factors. This inclination factor, the inclination of the load, resultant load to the vertical is say alpha in degree. Then we have IC equal to this 1 minus alpha by 90 whole square, and IQ is same as IC, and I gamma is 1 for phi equal to 0 and 1 minus alpha by phi for phi greater than 0. So these are the values of inclination factors given. And then next factor we need to consider is the effect of groundwater table position. Now let us see how the position of groundwater table affects. What does it affect? If I have the groundwater table somewhere, we know that the soil above the groundwater table will be presumably dry, assuming that there is no capillary rise, and this portion below the groundwater table will be wet, and therefore it will affect the density of the soil, and this density is going to affect the surcharge portion of the bearing capacity and also the weight of the soil. And that is why we assume that the bearing capacity has to be the surcharge portion and the frictional resistance due to weight of the bearing capacity portion, that means the N gamma term, and the NQ term needs to be multiplied by 0.5 or reduced to half if my water table is just at the ground surface. That is because for usual sands of normal void ratio of around 0.4 and specific gravity of 2.65, we know that the submerged density is nearly half of the total density, I mean the bulk density of the soil. That is why if I have a usual kind of sand, if the water surface rises up to the ground level, then the submerged density becomes about half of the usual density, and that's why this water table reduction factor in that case should reduce to 0.5. Now the water table, we assume that water table cannot affect the bearing capacity if the water table lies at a depth of df plus b below the base of the footing, because this density is going to be the bulk density in that case, not submerged density. And when everything is affected, then we assume that it is going to be 0.5. And that is why when the groundwater table is between the ground level and the foundation level, then we have RWQ, the surcharge term is 0.5 times 1 plus this depth d by this df, and the total cannot be greater than 1, so that when the water table is exactly at the base of the footing, then this value becomes 1, because this small d and capital DF becomes equal, so this term becomes 1, and therefore 0.5 into 2 becomes 1. That's why we take not greater than 1 here. So this portion due to surcharge is not affected, but this portion is of course affected. That's why we measure the depth here from this base of the foundation, which is called Z. In that case, RW gamma will be given by 0.5 into 1 plus Z by B. Once again, if Z is 0, that means the water is at this level, then this portion will be multiplied by 0.5. RW gamma is 0.5 because this becomes 0, and this is not affected. The question of D doesn't come at all, so it becomes 1. Okay. While using these equations, we need to take care that when there is water level at the foundation level, groundwater table is at the foundation level, this portion will be not affected, so it will remain as 1. Okay, because this D and this D will be same. So that's how this reduction factor for water table position takes into account the change in bearing capacity in this general bearing capacity equation. So I hope these things you have understood. Here we stop this part of the lecture, and next part we will discuss how to take the local shear failure into account. Okay, thank you.